Cool. Are we live? Yeah. Thanks for the introduction. So today we want to talk a bit about building and especially also standardizing an ecosystem for encrypted computation using the power of MLIR. And I just want to dive right into what is this encrypted computation, more formally known as fully homomorphic encryption, which is basically a type of encryption that lets you compute on the encrypted data and get meaningful results. And so the server can evaluate a function on encrypted data without learning the inputs, the intermediates, or the output of the computation.
Wait a minute, Alex. Surely at some point the server decrypts the data so it can see what it's doing, right?
No. This is an enclave. This is crypto. Even if you had perfect access to the registers, to individual wires, you wouldn't learn a thing.
Okay, there's got to be a catch. Is this just some theoretical curiosity, or is this real?
No, this isn't obfuscation. This is real and can be used to solve real-world problems. So the big sort of application is privacy-preserving machine learning. You get to run an inference over an encrypted input and get out an encrypted prediction, which has obvious applications to things like healthcare. But you can also do things like private set intersection. So you can use that, and this is deployed live in Microsoft Edge, so it has at least 5 users, to use to check whether or not your passwords have been found in some kind of darknet breach. You can also use it to do contact tracing, and this was actually deployed over in South Korea during the pandemic. And so we're seeing a first wave of actual real-world deployment.
Okay, it sounds like magic, but there's got to be some kind of cost, right? Is it you got to buy all this hardware? Is it slow? What is it?
Yeah, so FHE used to be slow. It's still slow, but it also used to be slow. It used to be much, much slower, though, than it is today. So back in 2009, Craig Gentry invented or showed for the first time that this was possible. And shortly after, we had the first implementation doing a single bit multiplication in 30 minutes. Thankfully, we've gotten ever so slightly better, and we're now doing this in, I think even this is an unoptimistic estimate. We're doing this much, much quicker. In fact, we're now doing real tasks. So back in the day, it took minutes to do basic machine learning like MNIST. Now we're doing this in fractions of seconds. And we moved on from these toy examples to slightly more realistic things like ImageNet and ResNet 18, which we can do inference on in perfectly reasonable times.
Alex, I'm still hung up on this computing on encrypted data. How could this possibly even work, even in theory?
Well, unfortunately, there is no magic functionality to just take a machine learning model and run it on encrypted data. What we do have is homomorphic encryption, i.e. a homomorphism between operations on the plaintext data and the ciphertext data. But the problem is, in order to qualify as a fully homomorphic encryption scheme, all you have to do is support addition and multiplication. And so that's still actually very, very hard to achieve. But we've known how to do this efficiently and securely for about a decade now.
Okay, so you have addition, multiplication. That's not very impressive. How do you use that to make programs?
With difficulty. So you don't really get branching. That's sort of not a limitation of the technique. It's just inherent in working on encrypted data. Branching leaks 1 bit of information minimum, right? And so you can't do that. In fact, all you get to do is arithmetic or binary circuits. Which is great because that's universal. But unfortunately, it's not just any kind of circuit, it's this noisy circuit, because this is integral to how we achieve the security of these schemes. We add some amount of noise, and this then grows as we compute. And if we don't really carefully manage this, we might not get the result that we were expecting. And so in fact, the majority of the cryptographic and computational complexity comes from having to manage this noise with specific ciphertext maintenance operations that don't change the message you're encrypting, they just do something with the noise. And so getting this right is very, very difficult. But if you do, you get all of these cool privacy-enhancing technologies that I just showed. And so my question to you is, why does Google care about privacy all of a sudden?
Well, let me tell you. So Google's got, as you might know, Google has a lot of products, has a lot of users, and it's got a lot of existing C++ code that they would prefer not to rewrite as a circuit, right? So we, could benefit from having more privacy-enabling features in all these products. That would be nice. On the other hand, there's a bunch of regulators who are coming to Google and saying you need to protect user data much better than you are currently doing it. So Google has a lot of work invested in satisfying these regulators, and it's also the right thing to do. And you might ask, okay, well, if these apps aren't going to rewrite their C++ programs as a circuit, what can you do? Well, you could make a new language. Google has no stranger to making new languages, but each of these languages up on there has like 30 or so engineers, right? And I've heard they even made like a whole new company for this language called Mojo. But the other hand is that, we could do a bunch of custom cryptography for each one of these things, but there's only so many cryptographers and there's all these other security breaches, and so crypto engineer expertise just like does not scale to the whole company, and so that's why we need a compiler to do privacy. Now, tell me, Alex, Intel does not have all the world's data sitting in its data centers, so why does Intel care about privacy all of a sudden?
Well, it turns out that this fully homomorphic encryption is rather computationally intensive. And so if you don't have about an internet worth of CPUs lying around, it's going to be a problem. And so Intel is developing dedicated hardware accelerators as part of this DARPA Deep Drive project that is aiming to accelerate FHE by 4 to 5 orders of magnitude compared to doing it just on the CPU. Because right now, while FHE is amazing, the cost is sort of prohibitive for more complex applications. And with this, we can vastly extend the range of things that you can use FHE on. In addition, Intel isn't just doing hardware, we're also actively involved in the crypto, and we're actually driving one of the tracks of the ISO standardization process to get this crypto industry ready. And of course, we're also trying to build and foster an ecosystem around encrypted computation.
Wow, these things sound really cool. If only there were a way that you and I could join forces and work together somehow.
Yeah, I think somebody should start like a working group. Oh wait, I did.
Yeah. Right, so we have a working group. We have a open design meeting every 2 weeks, and we're getting participants from sort of all over industry and academia. If you'd like to join us, there's a QR code that goes to our calendar. So we've got Google and Intel, we've got a bunch of FHE specific startups and universities and hardware engineers and MLIR experts. Anybody? Yes, come join us. I think at this point it's like, okay, we've got all this FHE stuff we want to do, but what's already been done out there, Alex?
Yeah. So unfortunately, we've been lying to you. There isn't one FHE. There is many FHEs. There's many different schemes, and they roughly fall into 2 very different camps. And this has been sort of how the community has seen itself. But thankfully, when you look at the underlying math and what really is the core of everything, it turns out that they all use this lattice-based cryptography, which basically means doing math in very specific polynomial rings. The underlying hardness assumption, if you're interested, is called ring learning with errors. So if you have your Diffie-Hellman kind of discrete log assumption, this would be the sort of post-quantum equivalent of that. And you would expect now that, we know that, this is like the math for FHE, the ecosystem should be pretty unified. Unfortunately, not quite. We have many, many FHE compilers, and actually quite a few that already use MLIR, and they're all re-implementing variations of the same wheel with slightly different context and slightly different trade-offs. And there's a good reason why we see so many compilers, and that's because as we are seeing crypto advances plateau off, and we're seeing hardware on the horizon, we somehow still struggle to develop efficient FHE applications practically and economically. And so this is what FHE compilers are trying to solve, but unfortunately, all of the existing ones struggle to achieve this on their own. And so if you think about the end-to-end pipeline of what it takes to go from an input program all the way to the hardware, be it via LLVM or to something custom, you really have sort of 3 separate stages. And we'll get into what that looks like when we talk about our lowerings. But what I just want to highlight is that we have all of these tools, some of which I've written, that go and do most or some of this, some more, some less. But as you might notice, none of these actually get the colorful blocks to connect from A to B. And so what we really have is a variety of things, some of them unfortunately clashing with our naming, that all do most or some of the things, but we still have a lot of hard parts left. So to really get an end-to-end FHE compiler, we need to, have some standardized abstractions, but we also need to solve some really, really hard problems. Some of them are more cryptographic, like these scheme switching things where you want to go from one scheme to another. Some of them are more involved in the front end side of how do you represent these programs. And the one that we want to talk most about today is how do you make the core polynomial arithmetic fast?
Yeah, so if you couldn't tell earlier, I was pretending I didn't know anything about FHE. But so the way I pulled these two formulas from some papers because deep down in the crypto papers, if you get to sort of the computational core, it turns out to be mostly tensor multiplications of structures that where the individual operations are polynomial multiplications in the particular ring. So sometimes it's sequentially accumulated loops of these things. Sometimes they're sort of SIMD parallelized, but like 95% of the workload is just doing polynomial arithmetic in some fashion. And so the first thing we started to do was make some explicit representation of this in MLIR. And so we have this poly dialect. Last night we were informed at the round table not to call it poly. And so we put the nomial after that. But so some of the code will say poly, okay, we couldn't update all the slides. But yeah, so polynomial specified by sort of its coefficients, but also there is an underlying ring where the math is happening. And we represent that by having some attributes that say, okay, what are your coefficients taken modulo what numbers, and what's the sort of polynomial modulus happening there. And that will give you some like math object that looks like this. And when we specialize it to cryptography, we get this very particular polynomial modulus. This basically says that x to the n is equal to -1 if you are reducing some polynomial. And this is like really security critical. If you change that plus to a minus, the crypto's broken, right? The degree here is also very important because it presents a security performance trade-off that you have to navigate. And then the coefficients, like what math you use on the coefficients, also has like a bunch of choices you have to make. They might be like 800 bits, and then you have to figure out how to like do some sort of residue number system to break them apart. They might be machine word size, in which case the number 2 doesn't have an inverse, and that causes problems with like polynomial long division. And then there's like algorithms like FFT and NTT where you have to be very particular about what you choose here, or the algorithms won't work out, or they won't be fast, or both. And so like there's like a bunch of crypto papers written about like each of the little symbols in this formula that like we have to sort of parse and figure out how to turn into appropriate compiler optimizations. And so we also want polynomial to be like a general thing. We don't want it to be specific to like just this one particular cryptographic ring. There's a bunch of other things, even within crypto, there's a bunch of other people using polynomial arithmetic to implement cryptography in interesting ways. We'd like them to be able to use this. And then there's also like the chance that crypto will change, right? Like maybe this particular ring will be determined insecure and we have to like change it to some polynomial with like 3 terms. And we want to be future proof for that. So we want to have the compiler sort of be more general. Yeah, and then at the round table last night, we had some additional ideas about how polynomials could be used in polyhedral analysis, blah, blah, blah. Okay, talk after. So now I'm going to get into a little bit of what the actual lowering looks like. I'm going to speed through some of this because there's a lot of details. The main thing I want to emphasize is that there's lots of optimization choices to be made at each step of this lowering, and they kind of bubble up and down, and we are still not entirely sure where to draw all of the lines. Oh yeah, and then the second line of green things is all the different FHE schemes, their initialisms based on the authors. Yeah, so at the very top we have like an input program. It's going to need to annotate some things as being secret or not secret. And then the question is like, okay, well, how do we represent operations on secret things? Some of the prior art has like had like shadow arith dialects that just replicate all of arith, but on like secret things, and we prefer not to do that. Making our own thing is too much effort. We can't reuse existing MLIR passes on those things. Using arith itself is not good because even though we could reuse stuff, arith doesn't support anything except integers and tensors of integers, or tensors of numeric types. And so instead, what we did was we said, okay, well, really what we want to do is use normal MLIR on the underlying clear text and like wrap it in some semantics that say that here is the operation that's happening semantically, but like actually it's happening on secret data. So we made this, and so that's just like a little preview of that. And then the question is, well, you have some secret type. How do you lower it to, you have to pick which scheme you're going to use, right? And when you're going to switch between schemes. And some of the schemes only support like small number types. Some of the schemes are better when you're sort of vectorizing things. And some of the schemes, well, just by using the scheme, you incur some approximation inaccuracy, right? And so you have to like comprehend with all those things. I'm just going to pick one, right? This one called CGGI that I'm pretty familiar with. And even there, it's like, OK, if you just have some number and you want to multiply them, you have kind of a bunch of weird options. CGI has this thing where you can, one of the noise management operations also allows you to evaluate a lookup table. So you can implement things like multiplication with this cheeky trick that does a lookup table for a squaring operation on 4-bit integers. And then like you do some other stuff. And the other stuff is kind of tricky because, as you can see with the asterisk, it adds noise when you do those operations. So you have to be sensitive about like, how you stack these things together. Down inside there, OK, so the last slide was like sort of the public API of the ciphertext, how you write programs in that crypto system. This is more like the implementation of the crypto system for cryptographic operations that have no meaning to you people, but they add noise, and there's a decision about how to order them that affects like the key sizes and all of this other stuff. Going a little bit fast just so we can get to some more stuff after this part. Yeah, so OK, inside one layer lower, there's sort of like a big loop where it's doing this sort of private CMUX operation. And then one step lower, you'll see down at the bottom, there's like, it decomposes to like a big tensor mole of polynomial operations. And you'll see these comments that say like 90% runtime, 90% runtime. That's because like it's all in the polyops. And then now there's a question of like, OK, well, how do you actually implement polynomial multiplication? On CPU and GPU, you have the option to do like FFT-like things. On TPUs, you don't even get FFTs with enough precision to do that, so you represent it as like a big old map mul. And all of these decisions depend heavily on like which ring you're using, which types of like fast polynomial multiplications you can implement. So OK, I'm very tired of that. Why don't you take us a step back and synthesize that?
Yeah, so you saw a bunch of lowerings fly by really quickly.
Yeah.
And I think one of the interesting things compared to a lot of the other lowerings you might have seen yesterday and today is that it's not so much that we're doing some clever tiling, we're not doing some clever memory management, right? Just the inherent semantics of the lowering are like somebody got a PhD for that, right? And this is one of the challenges for us, and I'm going to skip a slide here actually real quick, that there's just not a lot of people that can both write these lowerings in C, C++, in MLIR, and actually pass them from a LaTeX crypto paper. And so jumping back to where we're supposed to be, what is the issue here? Well, there's a bunch of things that the compiler has to do just to be an FHE compiler. And that's be good at fast polynomial math. It needs to have an idea of the noise. It needs to respect it. That can be some hard coding, or it can be some cost model and optimization. It needs to help with the security parameter selection. I think Jeremy quickly mentioned that there's like these tweaks that you can do to the ring, and like they have a big difference on your computation. And this is something that actually is kind of hard. It needs to do all the data movement and static scheduling. We mentioned earlier there's no branching in encrypted computation, but that means that also there's no need to use any of the hardware's like sort of like live branch prediction, whatever. And there is an expectation that any compiler that targets this will be doing perfectly optimal static scheduling as far as possible. And then there's this whole bag of performance tricks that the community has established. I think for time reasons, I'm going to skip going into these, but the idea here is that none of these are better or worse than any other. Even where the ones where we're like 99% sure they're not amazing, there is a pathological use case where it's the best one to do. And so it's really hard as a compiler developer to say, oh, I'm only going to implement these three because they're the most important ones. It seems like we will have to implement all of them and then find some kind of cost model and analytical model of FHE in order to select between them. OK. And so we have a bunch of really interesting challenges, at least interesting to us, that we would love people to start looking at either on their own or ideally with us. And so one of the things is data flow analysis in multi-entity, multi-party encrypted systems, right? Where data can suddenly be private to some person, but not private to another. And there's huge optimization potential in getting this right and analyzing this efficiently. There is, as I mentioned earlier, this whole issue of noise and the various trade-offs you need to make. And we really want to be able to express these noise in some way in the IR, have analyses that operate on that natively. But that requires both crypto and compiler work. And one of the things I think Jeremy said, like, we're not quite sure where to draw the lines. And one of the issues here is where do we stop pretending that it's crypto and just do number crunching on polynomials? And then we have all of these like fun hybrid schemes and all of that good stuff that makes this challenge even more complicated. But if we do all of that, we will end up with the ability to lower pretty much any FHE scheme to really efficient LLVM. And hopefully, we'll find enough people in this intersection to actually do this. But ideally, it would be great if MLIR wouldn't quite require so much expertise, because there's a lot of people who can read crypto papers, right?
Enough, yeah.
Yeah, but teaching them MLIR makes their crypto PhDs look like kindergarten.
Yeah. Well, so sort of some of the lessons we've learned along the way that we want to pass back to the MLIR community, because we're sort of all learning MLIR as we go, and sort of trying to figure out how to do good dialect design while at the same time making FHE fast and useful. And so we found some sort of, generally the feedback is very positive in the FHE community, right? People don't want to write their own compilers. They will if they have to get a PhD, but they find it very helpful to have a lot of the infrastructure there for them, right? Generally very positive. So the points on these slides on the next are going to be more nuanced specific points. So basically when we're trying to design these dialects, the process of designing the dialect is a type of formalization, right? So it helps us figure out where are the gaps in our knowledge, where are the hidden assumptions, where are the details left to the reader in the math papers. The existing proof of concept and just one path through the graph FHE compilers have also given us enough confidence that this is going to work, right? It's just going to take enough time and effort, but we're going to get something that's production worthy. It's going to be fast. The accelerators are coming, right? There's nothing really in the way that's preventing us from doing this right. And since those other projects were already written in MLIR, we can reuse some of their code. We can glue them together. So it's a very nice interoperability story. On the downside, MLIR is kind of hard in some ways. Hard for crypto people who just write all of their stuff in Sage Math. And getting people to have the conversation in the MLIR lingua franca is a bit of work. And the learning curve for MLIR is, the documentation could use some improvements, but more nuanced than that, right? There's a lot of ways to do things, and there's not a lot of opinions about the right ways to do. Or you all have these opinions, right? But we have to come here to talk to you to learn them, right? And it would be nice if if we could read them somewhere and refer to them sort of statically. And so we talked to a bunch of people in the FHE community who worked on MLIR stuff. And we got some quotes from them that might be of interest to you. One of them that we sort of faced when we were working with secret data types is the top left one that upstream folks kind of assume that you're working with very particular types of data. And it would be nice if we could reuse more of the upstream stuff if those assumptions were not there. In our case, it's encrypted analogs of arithmetic. And then, I don't know if you have any additional thoughts on some of these quotes.
I think a big one is that a lot of the early documentation was written in an analogy to LLVM. And I think as we see in the program of this very event, there's a lot of people that are here for the MLIR nowadays, right? And so I think we should maybe go back and rewrite some of this early documentation. And I think Jeremy has a few things to plug here.
Oh yeah, I started writing some MLIR tutorials because people in the FHE land were I tried MLIR. Yeah, actually I talked to someone specific who was we tried for a while to use MLIR and we couldn't figure it out. So we just built our own compiler from scratch. And we were oh no. But so, I'm trying to bring some of these people into the community by teaching them how to use MLIR. And I think it's working. But yes, okay, so here's our closing slide. We want people from the MLIR community to engage with us. With all of these ideas, you probably have ideas for how we should solve them, and we want to hear from you. We have meetings. We have a RFC on upstreaming the poly dialect, and the details of that are available on Discourse. Please keep us out-of-tree mortals in mind when you're designing your upstream stuff. And yeah.
Yeah, thanks for having us.
Thank you.
No time?
What?
Oh, one question. Don't so much have a question more than a comment. Then you're asking people from MLIR community to come to FHE. I invite you to come to MLIR. You already started, and I know there's tutorials. Please contribute them to MLIR. Like people who know MLIR really deeply can, I think, no longer explain to people who don't. Like, I don't really know what you don't know about MLIR. I know so much about, like, yeah, that's how this thing should be structured and so on and so forth, that if you struggle with something, I'm sure other people also did. So just write that down, put that in the documentation, submit, I'll click your patch, it will be landed tomorrow, and everybody will be happy.
We should have time.
Thanks for the talk. I would like to echo what Alex was saying. Please come to us. Thank you for the RFC. I don't know who sent it, but it's interesting. Thanks for the bug reports, Jeremy, and the patches you sent already. Very much appreciated. We have a weekly open meeting in MLIR, which is really open, meaning most of the time we don't have anything on the agenda, so I just cancel it. But if you want to talk about FHE, even in a non-structured way, which is like, hey, I'd like to gauge interest about this, just bring people. We can have discussions between people who know MLIR and people who know FHE or whatever, and have unstructured discussion and start to build collaborations or whatever. On the documentation and the approachability of MLIR, it's also very hard for us who are experts in MLIR to document it in a way that is accessible to beginners. So we try to do tutorials, we try to do things, but with the mentality of compilers. So it's more like compiler engineers talking to compiler engineers. Hey, here's how you use the compiler. But I think it's with MLIR trying to get into DSLs and domain specific like FHE. We would love to be able to be more approachable for people from domain specific fields. And it's just that maybe we are not in the best position to know how to do that. Or if we get more data and information about how to do that, we'll do. So anyway, thanks for proposing all of that. Very exciting direction.
Thanks. Yeah, we'll definitely be at coming to an ODM near you, right? Like we're planning to present Poly and the RFC in one of the upcoming slots, hopefully.